So, what if I told you there's a secret map for matter itself? A kind of cheat sheet that tells you exactly how any substance is going to behave under any condition. Well, today, we're unfolding that map. We're going to explore the states of matter using just two coordinates, temperature and pressure. We all learned the big three in school, right? Solid, liquid, gas. Seems pretty straightforward. But is that really the whole story? I mean, what happens when you seriously crank up the heat or apply some absolutely crushing pressure? Well, that's when things start to get wonderfully weird. See, at its core, the state of any substance is just this constant tug of war. On one side, you've got kinetic energy. That's the energy of motion. You heat things up, and the particles just want to zip around and fly apart. But pulling in the other direction, you have these intermolecular forces. That's the natural stickiness between molecules, trying to hold everything together. The winner of this epic battle determines everything. So to really get a handle on this tug of war, let's do a quick refresher on the states we think we know, but let's look at them through the lens of that epic molecular battle. Okay, take a look here. In solids, over in that first column, those sticky intermolecular forces are winning big time. The particles are locked down tight. Then, in the middle, you have liquids, where kinetic energy has loosened things up just enough for particles to slide around. And finally, over on the right, you've got gases. Kinetic energy is the undisputed champion here, with particles just flying totally free. So, how do we predict who's going to win this battle under any given condition? Simple. We need a map. And lucky for us, chemists have already drawn one. It's called a phase diagram, and it is our ultimate guide to the states of matter. Seriously, think of a phase diagram as a treasure map for matter. You just point to a temperature on the bottom axis, a pressure on the side axis, and bam! The map tells you exactly what state you're in, solid, liquid, or gas. It's that powerful. And here's what a typical one looks like. You see those three big regions? Down here in the cold, high-pressure corner, that's where you get solids. Way out in the hot, low-pressure territory, you find gases. And liquids? Well, they live in that sweet spot right in the middle. But the really interesting parts are those lines separating them. That's where the magic happens. Okay, let's break this down. Every good map needs landmarks, right? On a phase diagram, these boundary lines are absolutely crucial. Crossing one means you're triggering a phase change. We're talking melting or boiling. Then you've got this totally one-of-a-kind spot, the triple point. It's the only temperature and pressure where something can be a solid, a liquid, and a gas, all at the exact same time. And finally, way up on the top right, that's the mysterious critical point. It's kind of like the edge of the known world, where all the rules start to break down. All right, enough with the theory. Let's put our new map reading skills to the test with something we see every single day, water. But don't be fooled by how common it is. Water's map is hiding a truly bizarre secret that has literally shaped our entire planet. So here it is, the phase diagram for water. Now look closely, I mean really closely, at the line that separates the solid region from the liquid one. See that? It slopes backwards, to the left. For almost every other substance on Earth, this line slopes to the right. This one, tiny, weird detail about water's map, has world-changing consequences. And that strange backward slope? Well, it's the answer to some surprisingly big questions. Ever wonder how a billion-ton glacier can flow like a river of ice? Or why an ice skate glides so effortlessly? The secret is written right there, in that one quirky line on the map. So here's the crucial point. Because of that backward slope, you can do something absolutely incredible. If you take ice, keep it below freezing, and then just squeeze it really, really hard, you can actually force it to cross that line and become liquid. You can literally melt ice, not with heat, but with pure pressure. And this is how we solve the glacier puzzle. The colossal weight of a glacier creates immense pressure at the very bottom, and that pressure is enough to melt the ice, creating this super thin layer of liquid water. This layer acts as the perfect lubricant, letting the entire mountain of ice slide downhill. It's incredible. A planetary scale phenomenon, all because of one little line on a chart sloping the wrong way. So water is clearly a bit of a weirdo. But to really appreciate how weird, let's compare its map to something else. Let's look at the case of carbon dioxide, or as you probably know it, dry ice. Okay, check out the phase diagram for CO2. Find the triple point. It's right there at a pressure of about 5 atmospheres. Now look lower down that pressure axis, all the way down to 1 atmosphere. That's the normal pressure we experience every day. You see how it's way below the triple point? This simple fact means that under normal, everyday conditions, it is physically impossible for CO2 to exist as a liquid. Now, what's really fascinating here is the stark contrast. On the left, if you heat regular ice at normal pressure, it travels that familiar path. Solid melts to liquid, and that liquid boils to a gas. But look at the path for CO2 on the right. At that same pressure, it does something totally different. It jumps straight from solid to gas, completely leapfrogging the liquid phase. This direct jump from a solid to a gas has a name. It's called sublimation, and it's why dry ice is dry. It never makes a puddle. It just seems to vanish into thin air as it turns into invisible carbon dioxide gas. And once we understand this process, we can use it to do some pretty amazing things. Take freeze-dried food, like the ice cream you see here. To make it, you freeze the food, then stick it in a powerful vacuum. This drops the pressure way, way below water's triple point. Now, the ice inside the food doesn't melt, it sublimes, turning directly into vapor and leaving behind perfectly preserved lightweight food. It's pretty much science magic.
Okay, so we've navigated the familiar lands of solids, liquids, and gases. But remember that mysterious critical point I mentioned? The one at the very edge of the map? Well, it's time to venture into that uncharted territory, beyond the boiling point.
If you look at any phase diagram, that line between liquid and gas, well, it doesn't go on forever. It just stops. So what happens if you take a substance and push it past that point, into that super high temperature, super high pressure zone? Is it a liquid? Is it a gas? Or is it something else entirely? Well, you get something incredible, a supercritical fluid. This is a fourth state of matter, a bizarre hybrid of liquid and gas. As you can see, it expands to fill a container just like a gas, but it can dissolve things just like a liquid. The very distinction between liquid and gas just ceases to exist. It's a whole new state of being for matter. And this isn't just some lab curiosity. It's probably part of your morning routine. The most common method for decaffeinating coffee uses supercritical carbon dioxide. It's heated and pressurized past its critical point, and in this amazing state, it can seep deep into coffee beans like a gas, but then dissolve and carry away the caffeine just like a liquid solvent would. And this is why it's such a brilliant process for industry. It's incredibly effective, pulling out almost all of the caffeine. But because CO2 is so gentle, as you see in the second point, it leaves all those delicate flavor and aroma compounds behind. Best of all, it's completely non-toxic. When you're done, you just lower the pressure, the CO2 turns back into a regular gas, and the caffeine literally just falls out. It's clean, it's clever, and it's all thanks to that weird spot on the map. So, from the weight glaciers move, to the astronaut ice cream we eat, to the decaf coffee in your cup, these phase diagrams are so much more than just charts. They really are like cheat codes for matter. They show us that by mastering the simple rules of temperature and pressure, we can make substances do these incredible, totally unexpected things. It just proves that there are hidden rules and surprising possibilities all around us, just waiting to be discovered. So the real question isn't just what's on the map, but what other maps are we still waiting to draw?